Hello, everyone. This is Kyle Welch with RCR Wireless News. I want to thank everyone for attending Adapting Maintenance Techniques to Current Trends in LTE Installations, presented by Anritsu. Our presenter today is Andy Stanton, Product Manager at Anritsu. At this time, I'd like to turn the presentation over to Andy.
Thank you, Kyle, and welcome everyone to this presentation, Adapting Maintenance Techniques to Current Trends in LTE Installations. The agenda for the day, first we'll take a quick look at the LTE market today, just to put everything into perspective. We'll then look at the evolution of cellular base station installations from 2G through 3G and now 4G. We'll then look at some of the issues today in relation to where technologies are installed on the same infrastructure and see what the concerns are there. We'll then look at traditional maintenance techniques and see how they've had to be adapted to cope with the new style of installations. We'll then look at what's going to happen in the LTE market in terms of newer and upcoming installations, and then the consequences from a test equipment manufacturer point of view, how to keep up with those changes. And then right at the end, we'll look at some measurement examples, specifically looking at some MIMO measurements, carrier aggregation. We'll look at consequences for geolocation services and also look at DAS integrity testing as well. And hopefully at the end, there'll be time for me to answer some of your questions. Okay, so this is the state of LTE subscriptions worldwide today, and you can see it's an upward trend, an exponentially growing trend, and you can see how that trend has changed over the last 3 or 4 years. At the moment, or as of half year this year, there are about 280 million LTE subscribers globally, and that sounds like a big number, and it is a big number, but if you put that in the context of the proportion of subscribers of all technologies, that represents just 4% of all cellular subscriptions. So LTE has got an awful lot more growing to do and will have an awful lot more growing to do, and I don't see any reason why that trajectory should change. Now, of course, to support all those subscribers, the infrastructure needs to be there already, and that's why we're seeing such a huge rollout and growth in infrastructure for LTE support. If we look at that on a global scale or regional scale, you can see that the largest number of subscribers in North America, and there's a good reason for that. The USA was the first to release lower frequency bands, specifically the 700 megahertz band, and that's very attractive to roll out a cellular network quickly because the propagation properties of lower frequencies are much better. They propagate further, and more importantly, they can propagate into buildings quite easily as well. So you get very good coverage very quickly with lower frequencies. Now, the rest of the world has been a little bit slow to release the lower frequencies, so that's why the rest of the world is lagging behind. But I will say that the fastest growing region in the world at the moment is Asia Pacific, and I predict in about 2 years' time, the number of subscribers in Asia Pacific will be greater than those in North America. So just to put that in perspective in terms of the number of networks worldwide, the red areas on that map are regions or countries which have commercially viable, commercially operating LTE networks. The blue ones are in trial at the moment, and the light blue ones are planning to have networks in the not too distant future. So at the moment there are 331 commercial LTE networks in both FDD and TDD technologies worldwide. So huge potential for growth of subscribers, huge potential for growth in infrastructure. So now if we look at how we got there, LTE, and look at traditional base station installations, GSM is still the majority infrastructure technology. There are still many more GSM subscribers than any other technology in the world, and that constitutes the major infrastructure technology out there. Interestingly, 3G is still not completely amortized. What I mean by that is the investment that operators put into 3G infrastructure and technology has not been clawed back yet because of us, basically. The demand for high throughput, high data rates meant that 3G technology was not good enough to support that. So then they've had to migrate quickly to 4G LTE technology to cater for that demand. Interestingly, looking at 2G, 3G and 4G, again to facilitate fast rollout of networks, there is a lot of site sharing of different technologies. So operators that have both 2G, 3G and 4G licenses are using the same physical infrastructure to install all technologies. Sometimes they're sharing infrastructure that's already there and multiplexing onto the same RF feeders, the different technology signals. And sometimes, in some cases, even operators themselves are sharing the same RF infrastructure. And LTE rides on the back of that. To facilitate fast rollout, LTE usually initially uses the same infrastructure sites, the same cell sites that the older technology used, just so it can get fast rollout up and running quickly. Okay, so a review of traditional installations. Back in the 2G days, radios were installed typically in cabinets on ground level, usually in environmentally controlled chambers, and the antennas were fed by RF feeders at the top of a mast. Rooftop installations were similar, where the radios were housed in cabinets inside the building, and then RF feeder cables were taken from there up to the roof to feed the antennas. With 3G, the introduction of remote radio heads was a feature, where the radio part now was remoted from the radio control part up near the antenna. And the remote radio heads were fed usually by fiber from a base station server housed somewhere in the building or somewhere in the city. The advantage of that was that the long feeders that were used in traditional installations were no longer required, so the losses involved between the radio and the antenna were much reduced. And the other notable thing about traditional installations was that in-building coverage was really covered from external base stations. Base stations external to the building were used to illuminate the interior of the building. And that's a change that's happening with LTE. For remote radio heads, as I said already, the reason that they become popular is because in traditional installations, the loss in the feeder from the radio to the antenna can be as much as 3 dB, sometimes more. That means that at least half the power that's being transmitted by the transmitter is being lost before it gets to the antenna. So that means that the size of the cell is reduced, and the signal-to-noise ratio within the cell is reduced as well. Now, with a remote radio head where you've got the radio much nearer the antenna, you can gain back all that lost power. So you can either use less power to illuminate the same area, or you can use more power to illuminate a larger cell area. So that's the reason why remote radio heads became popular. So the benefits, they save power, and that's important from an operator's operational cost, but also important from the obligation on operators to be green and to reduce greenhouse gases. So reducing power obviously helps towards that. They also save costs, and they also improve spectral efficiency. But there are concerns, especially in the early days of remote radio heads. There was concerns about the reliability, because now, of course, the radio is installed external to the cabinet. It's open to the environment. It's open to the rain, the snow, the sunshine. So there were concerns that the reliability of these remote radio heads would be compromised. And that kind of stalled the initial rollout of remote radio heads. Also, accessibility for maintenance. If you've got now a radio installed at the top of the tower, you now need qualified people to be able to climb the tower, to be able to get up there to maintain the remote radio head. And the other aspect, of course, is that when you're adding more infrastructure to the tower might not originally have been built with further infrastructure to be built on it in mind. So therefore, there could be some loading issues, some wind loading issues that need to be taken into account. So all of that kind of is the reason why remote radio heads are now being used, but also the reasons why, you know, they had a slow start before they were well accepted in the arena. This is one of the problems with infrastructure sharing. At the bottom left-hand side there, you can see that maybe old 2G construction is now being used to support both 3G and LTE services. So to add all that in, you need feeders, you need tower amplifiers, you also need more antennas to support the different frequencies and the different technologies. Now, all that extra equipment can cause problems, as I said, weight and wind load issues. So you can get around that somewhat. You can combine a lot of the technologies onto the same feeder. So on the bottom right-hand side there, you see LTE, 3G, and 2G technologies being combined onto single feeders and then split at the top and then fed to multi-band antennas. Therefore, your weight and wind loading is reduced. However, you might be using infrastructure that was originally used for 2G technology, works well at 2G frequencies, but may need to be retested and requalified at different frequencies. The other aspect of that is that when you combine multiple frequencies on the same infrastructure, there is a much higher potential for something called passive intermodulation. And let's take a brief look at what I mean by that. So what is passive intermodulation? Well, PIM is new frequencies generated by transmitter signals at a cell site when they encounter nonlinear junctions in the RF path. And I'll talk a little bit about what I mean by nonlinear junctions in a minute. And if that PIM falls in an operator's uplink, it can raise the noise floor. It can desensitize the receiver of a base station. And that will result in potentially drop calls or denied access or throughput issues, which is really problematic. What do I mean by nonlinear junctions? Well, this is a photograph inside a connector, and you'll see inside there's some metal flakes. Now, every time you mate a connector and demate a connector, some metal will rub off the connector and fall inside that inner connector there. Now, if you then mate that connector with a feeder cable, any of those metal flakes that touch the outer or inner conductor will cause a nonlinear junction and cause passive intermodulation products to be generated. This is another example of a nonlinear junction where connector pairing has not been tightened properly. It's only been hand tightened. In that case, there could be a gap between the two connectors, and that gap, when it's exposed to high RF energy, can arc and cause passive intermodulation products to be generated. So again, good installation practice is to make sure all connector pairs are torqued correctly to reduce the possibility of any PIM being generated. Now, unfortunately, PIM is not only restricted to inside the transmitter system itself. PIM can be externally generated. So in this example here, you see you have a base station here with the two antennas. That could be totally PIM-free. The RF network behind these antennas could be totally PIM-free, but the signals are radiating some metal here. And you'll see at the top of this roof here, you've got some metal flashing. If there's any corrosion in that metal, it's likely that when it's exposed to high energy RF power, that will produce passive intermodulation products and be reflected back to the antennas in the receive path of the system. So unfortunately, PIM can both be internally generated, but more problematic, externally generated as well. This is what PIM looks like at the site. So here we see two WCDMA signals on the uplink side. This one here is PIM-free. This one here is being exposed to some passive intermodulation products produced by a co-sited GSM system. And you'll see these narrow band spikes here associated with GSM. This is going to desensitize the receiver and cause problems for this channel here. What it looks like from an operator's point of view, this is time along the x-axis here. So if you have a PIM problem, it's likely that your residual noise floor of your receiver is quite high. And it will vary slightly. It might get a little bit higher when you're busy and a little bit lower when it's quieter. But this is pretty bad at -93, -94 dBm. So if we implement a PIM repair here, you can see you can get back, in this example, about 13, 14 dBs of sensitivity in the receiver, which makes a huge difference to the performance of the base station. So that just shows you a practical example of how PIM can desensitize the receiver. The other aspect to note as well is that the intermodulation product's bandwidth is proportional to the bandwidth of the transmit signals that are producing it in a bad way. And to give you an example here, look at these two 200 kilohertz signals, F1 and F2, being transmitted by the transmitter. This would typically be GSM signals. The IM3 products are 3 times wider, the IM5, 5 times wider, etc., etc. So if you think about today with LTE, where the potential to have 20 megahertz channels is there, if you have two 20 megahertz channels being transmitted, the potential for intermodulation, passive intermodulation signals to be present in an uplink receiver band is very, very high, because the third order will be 60 megahertz wide, the fifth order will be 100 megahertz wide, right the way up to the ninth order, which will be 180 megahertz wide. So the potential to cause problems is much, much greater the wider the bandwidth of the signals as in LTE. I guess it's appropriate now to just say that Anritsu does produce PIM test equipment, portable battery-operated PIM test equipment covering all bands. And the other important thing as well is that it has a patented distance to PIM problem. It's quite easy to determine whether or not you've got a PIM problem. You can do that with a spectrum analyzer. The trick is to be able to locate it quickly, and that's where that patented distance to PIM function comes in, because it can pinpoint exactly where the PIM is coming from, either inside the system or even external to the system as well. Okay, so let's look at the traditional maintenance technique. And, you know, operators and third-party contractors use this technique traditionally. You can either do measurements over the air, once you've found a valid over-the-air spot, and we'll talk a little bit more about how to do that later. Or in traditional installations, you might have a test point directly at the transmitter, so you can directly connect to that transmitter test port to do measurements. You would then typically go through a sequence of tests to determine whether or not your base station is optimized or running okay. And you can specify your test limits for each of those tests in a pass-fail test scenario. If that passes, that's great, the transmitter's working okay. Typically what you then do is check the throughput, and with a PC, and if the throughput's good, great, done, move on to the next one. Anywhere in that process, if you have a problem, something fails, you then might need to troubleshoot maybe the feed lines or the base station amplifiers. There might be coverage issues, or there might be interference issues that need to be debugged. And also, of course, if you have throughput issues, you might need to look at the backhaul as well. So that's traditionally how maintenance was done. Now, different operators use different philosophies. Some operators use a system of preventative maintenance, where on a regular basis they will go out to each base station in turn, maybe every 6 months or every year, run through a sequence of tests just to make sure that everything is still optimized. They will compare those measurements they've just done with what they did 6 months or a year ago. If there's any downward trends, they can then take corrective action before it becomes a catastrophic failure. That's one method. Other operators might use a fix after failure method, where they don't do any maintenance and rely on key performance indicators like drop calls or access denial or throughput issues to determine whether or not a particular site has an issue, and then go out and fix it. Pros and cons to each. It's entirely up to the operator as to which one they use. This would be a typical pass-fail example here, where you would select the measurements that you're interested in. For example, here we've got channel power and occupied bandwidth, frequency error, etc., etc. You would define the limits of that test to determine whether it's passed or failed. And once you've selected all your tests, you would then just press the button and you'd run through the sequence of tests. And at the end of it, you get a report saying either you passed or failed. And depending on what's failed, you then need to go in and do some further investigative diagnostic work. The advantage of using the pass-fail method with defined limits is that you can then test every base station to exactly the same parameters. so you get consistency throughout the network, and that ultimately will improve the performance and quality of your network. The key performance indicators that operators use, as I described before, session blocking or session drops or throughput issues, they are caused by various different things. So, for example, a session block could be caused by a resource block shortage in LTE. If that's the case, the most likely parameter that will be out of specification or bad would be the EVM, error vector magnitude, or the modulation quality. And there's a good reason for that, because with a resource block shortage, if the EVM is bad, typically what happens in LTE is that lower modulation schemes are used. Rather than 64 QAM, they use 16 QAM or QPSK to adapt to the bad radio conditions. Now, if that's the case, your throughput goes down because you're using a lower modulation scheme. If that's the case, particular users will use more resource blocks to try and get back that lost throughput. If they use more resource blocks, it means there's not so many resource blocks available for other users. Therefore, your overall capacity, your overall user capacity reduces at the site. So that's just one example how you can relate key performance indicators against a test to prove what is the cause of that KPI to fail. If you then look at the tests which are bad, you can then determine the most likely part of the base station which is failing. So, for example, in that example, where error vector magnitude was bad, the most likely component that's failed is the power amplifier. It might be nonlinear, it might be some issues with it that's causing compression, which will cause the EVM to be bad. So once you've identified, which measurement is failing, you can then identify the field replaceable unit that's most likely to have failed. So you take the card out, put a new one in, do the test again, and hopefully everything's fine. So that's traditionally how maintenance was done. I should point out here as well that Anritsu produces a whole range of troubleshooting guides for different cellular technologies, LTE, GSM, WCDMA, etc., whereby all the maintenance measurements are talked about, the guideline for the measurement, what the specs should be, the consequences of not meeting that specification, and the most likely area in the base station which is causing that failure. And I would recommend anybody who's involved in maintenance of base stations to download these and look at these, because they really are quite invaluable tools to help with maintenance techniques in the field. Of course, you might go through all your pass-fail tests and everything's working perfectly, but you're still getting some issues from your KPIs. Well, then the possible scenario now is that you have coverage issues. Now, most handheld equipment from Anritsu, which can be used for base station testing, also has some mapping capability as well, which you can use to look for dead spots or areas where coverage is bad. I should emphasize that this is not a drive test tool. It's kind of complementary or supplementary to a drive test tool. Sometimes when you've got coverage issues, you don't have access to a drive test system or drive test team to be able to help you out. It's nice to know that the equipment you've used to maintain the base station can also be used to do some fundamental coverage mapping tests to make sure that you've got good coverage. Okay, so we've looked at traditional installations, we've looked at traditional ground-fed antennas through feeders, we've looked at remote radio heads. Things are changing going forward as well to cope and cater for increased capacity. More cell sites are needed, so sectors are split, and also small cells will be used. And the easiest way to implement small cell coverage is to use active antennas, where now the radio part of the base station is actually housed inside the antenna itself. So there are no RF lines, no RF feeders up the antenna at all, because the radio is installed in the antenna itself. Now, each of those radios is fed again by a base station server, usually via fiber, but not exclusively. And that base station server can typically be hundreds of meters away, sometimes kilometers away from where the actual cell site is sited. And each base station server can serve many different cell sites as well. So that's something called fiber to the antenna, using active antennas. And in that case, over-the-air tests are the only possible way to maintain those, because there's no RF access to test the base stations. The only way to check the performance is to do what we call an over-the-air test. The other trends I alluded to before with LTE is that there is a desire to have better coverage within buildings. So now, rather than illuminating buildings from the outside with external base stations, we're now moving the base station into the building and then distributing that signal throughout the building through what's called distributed antenna systems. And it's an interesting fact, actually, that we call these mobile radio systems, but less than 10% of all sessions are done when someone is actually moving around. Most sessions are done when people are stationary, either at their place of work, or at home, or in some shopping mall. Therefore, we need good coverage within inside buildings. Not so bad when you're using lower frequencies, but some of the LTE frequency bands are up in the 2.5, 2.6 gigahertz area. Much more efficient to move that base station inside the building and distribute it via a DAS system. Okay, so as I said, we're experiencing market conditions which are changing. We're providing the insatiable need for network capacity, which is stimulating the growth for LTE. There are certain co-siting challenges to be overcome. New base station types like fiber to the antenna, remote radio heads, and new transmission techniques like MIMO are also creating issues for a test equipment supplier and for maintenance technicians as well. Carriers themselves are driving costs down. The maintenance costs are being driven down. That has a big impact on test equipment manufacturers, because we have to support that in some way and provide equipment that is cheap and quick and easy to use to get the measurements that they desire. Also, what's happening is, because of the multitude of bands and multitudes of technologies that are being installed, is there an increasing levels of interference. More and more of the spectrum is being used, therefore there's more chance that interfering signals will affect it. Now, interference measurement is a webinar all in itself, and I won't be going into too much detail about interference here, but I will say that RCR and Anritsu are hosting another webinar next week, which deals with interference measurement, interference hunting, and all the mitigation techniques required to reduce the effect of interference. And I recommend everybody listening here to join that one as well. The other aspect as well is that sometimes now we have no choice but to do regular maintenance, because it's a mandatory regulatory requirement in some countries around the world. So we have no choice now but to do some kind of preventative maintenance on base station sites to make sure that they are still conforming to the license agreement when they're installed. So, what are our responsibilities as a test equipment supplier? Well, we need to be ready with new methods and measurements when demand hits. We talked about the changing methods from direct connect to over the air. We have to make sure that there are tools and techniques on our test equipment to be able to support that. There are multiple standards being installed at the same site, so we need equipment that can support all the standards that are installed. We need high performance, of course. We need to make sure that, when we do the tests, that the integrity of the base station is not compromised by poor performance of the equipment itself. All of this equipment is likely to be used outside at some point, so it needs to be rugged and reliable. It needs to be portable if it's used in the field, that's obvious. And it needs to be adaptable and upgradable. As new techniques and new measurements are demanded, we need to be able to make sure that equipment can be upgraded by users in the field to support those new techniques and new measurements. And the last one here is something that Anritsu takes very, very seriously, and has done so right from the very first time we introduced field test equipment about 20 years ago, is that as far as possible, the equipment needs to automatically be configurable to the requirements, the test requirements that are out there. To give an example, with LTE, as far as possible, what we've done is enable users to just set frequency and bandwidth of the signal and the equipment will automatically configure itself to receive that signal. You don't need to worry about input attenuation, resolution, bandwidth, any other parameters to be set. The thing will automatically configure itself, and that saves an awful lot of time in the field, gives you peace of mind that the measurements you're making are optimized for the conditions of the signal it's receiving. And we take that very seriously because that has a big impact on the productivity of maintenance engineers in the field. Just to give you a couple of examples of ease of use, on the left-hand side here, you will see this box here, this red box here, which says auto range. This is what I meant just now when I said if you set the frequency and bandwidth of the signal to be measured, the equipment will automatically tune to that signal, measure its power, and adapt the front end in terms of amplification and attenuation to optimize the signal condition to give you good measurements. Something that the user doesn't have to worry about. Auto range will automatically configure the unit for you. The other one down here is cyclic prefix. I won't go into too much detail about what that is, just to say that in LTE there are two cyclic prefixes available, normal and external. The cyclic prefix is the gap between signals that are transmitted here. Usually it's set to normal, which is a smaller gap. For some applications like large rural cells, you'll have a wider cyclic prefix, a larger cyclic prefix, and also for broadcast, LTE broadcast applications, you usually use a larger or extended cyclic prefix. Again, the user doesn't need to know what kind of cyclic prefix is being generated by the base station. The units will automatically detect it and configure itself to support whatever cyclic prefix is being transmitted. Again, a big time saver and ease of use facility for field measurements. Okay, I talked earlier about finding a valid over-the-air measurement spot. And this has become more important now, especially with new systems where the only possible way to test them is over the air. Well, you need to be in what we call a sweet spot. I guess we should define what a sweet spot is. So at the point where you're measuring, you should ideally receive a reference signal power of better than -80 dBm. There should be low co-channel interference. That signals from other base stations, other cell sites in the vicinity at the same frequency. They should be kept as low as possible because they will look like co-channel interference to the signal you're trying to measure and will corrupt the measurement. Ideally, or typically, you should be at least 20 dB more dominant, the signal you're trying to measure, than any interfering signal, co-channel interfering signal. Ideally, you want to be in a position where you're only receiving the signal from the base station you're interested in testing, i.e. all other signals are not detected. You need to be in direct line of sight with the base station. I could put here about 500 meters from the antenna. Of course, that will vary depending on the type of cell site it is, whether it's a small cell or a macro cell. But you need to be in direct line of sight away from any large reflectors. And what I mean by that, I mean buildings or hills or trees or freeways with trucks going by, because any reflectors there could cause multi-path interference, which again could affect the integrity of your over-the-air measurement. We would always recommend to use directional antennas, and you'll see in the bottom picture there the guy using a directional Yagi, high-gain Yagi, pointing directly at the base station, and that will minimize the effects of any signals coming from other directions, including multi-path signals from the base station you're trying to measure as well. And hopefully, when you're in that position, you will then be receiving the reference signals from, say, a MIMO transmission of roughly the same power. And if they're not, well, then maybe we might have a problem with the MIMO, which we'll talk a little about in a minute. So here are some sweet spot examples. The top one there, this is where we're in a position where, unfortunately, we are receiving more than one signal from two different cells, cell ID 10 and 11 here. And you can see the dominance between them is very small, about 2 dBs, and you can see the corresponding EVM, over-the-air EVM measurement we're getting very, very poor, very, very bad. And that's because cell ID 11 is causing a lot of co-channel interference to the measurement. So we move around a little bit and we find a space now where we've got 20 dB dominance between the cell site of interest and the interfering one from another adjacent cell site. And you can see now our EVM measurements are getting better. Sometimes that's good enough, but if you're measuring, say, 64 QAM signals where the recommendation or the guideline is to have better than 8% EVM, this isn't really a good place to do to guarantee that measurement. So maybe we can move around a bit further and now find a place where we are only receiving one cell ID, and therefore you can see here our EVM from the base station under test here is now down to 3%. So you're now in an ideal, what we call sweet spot. Now you need a very, very good high dynamic range scanner to be able to determine the dominance, to be able to find a good place to do these measurements. And Anritsu has very, very good scanners in its handheld equipment to be able to enable you to find a perfect sweet spot to do over-the-air evaluation measurements of base stations. And this is the measurement screen that we would recommend that you use to verify the MIMO configuration. Again, you'll be in a sweet spot, and this measurement screen here is split into 3 parts. Up here you've got the scanner, where you're identifying what cell sites you're receiving. In this case, ideally, we are receiving just the one cell ID, which is perfect. In the middle here is our MIMO test screen. This is where we can now measure the average power of the reference signals, in this case of a 2x2 MIMO signal, and also measure the delta power between the 2 reference signals. And that can give you an indication of whether or not there's any MIMO issues. If this is too large, we might have one side of the MIMO is wrong, or if we are receiving 2 cell IDs and we can't find a sweet spot, and this has a large difference here, we might have cross-connected the MIMO signal from one sector to another sector during the installation. So this can be used as a MIMO troubleshooting tool as well. In fact, I should recommend this application note down here, which goes through troubleshooting MIMO installations in great detail. And right down here, you can see this icon here, which is indicating that we are receiving a MIMO signal. The equipment will automatically detect it's a MIMO signal and set itself up to measure MIMO signals. Again, the user doesn't even have to worry about whether or not it's a MIMO signal or not. The equipment will automatically detect it and respond correctly. And these 2 green antenna icons here are showing me that we are receiving a 2x2 MIMO signal. And in this situation here, good sweet spot, good RS delta power within 3 dBs, and we can do over-the-air EVM measurements, and we can characterize the performance of our base station under test. So that's typically how you would do MIMO verification over the air. One new feature or aspect of LTE was introduced in the LTE Release 10 specification of the 3GPP specification, something called carrier aggregation. And carrier aggregation is being rolled out in various parts of the world. I think Korea was one of the first countries to implement carrier aggregation. What is it? Well, traditionally, of course, each operator has one carrier with an associated bandwidth, whatever it is, 5 megahertz, 10 megahertz, 20 megahertz. And of course, that has limitations on the downlink capacity available to you. Well, if operators can get hold of more spectrum and more channels, they can now aggregate those channels or aggregate those carriers together to increase the downlink throughput. Okay, now those what are called component carriers can be from the same band or they can be from different bands. So you'll see examples here, and they can also be at different bandwidths as well. So you could have a 10 megahertz aggregated with a 1.4 megahertz aggregated with a 5 megahertz, for example. So the 3 possible scenarios are where you've got intraband, what they call intraband contiguous aggregation, where you've got, in this case, 3 channels aggregated together, which are right next to each other, i.e. contiguous. The next scenario is something called intraband non-contiguous, where you've now got, in this example here, you've got two channels in the same band and a third channel in the same band, but is not contiguous. It's not next to the other two. So that's intraband non-contiguous. And the final scenario here is that you've got interband non-contiguous, where you've now got channels in multiple bands, not contiguous in any band, aggregated together. Now, depending on which scenario you've got here, there are implications on the delays between the transmissions of those channels. Something called time alignment error. And in the bottom right left-hand side here, you've got the 3GPP specifications for the different allowable delays between transmissions in these three scenarios I've just described. So intraband contiguous 155 nanoseconds, intraband non-contiguous 285 nanoseconds, and interband up about 1.3 microseconds. And that is a key measurement in the field to make sure that everything is going to work correctly to be able to determine the maximum time alignment error between these component carriers. This is Anritsu's carrier aggregation measurement solution. So we can configure up to 5 component carriers. That's what the 3GP specification currently allows for, up to 5 component carriers. Each one can be as wide as 20 megahertz, so potentially you have 100 megahertz of downlink bandwidth available to you. This particular screen is showing 3 component carriers configured. One at 5 megahertz, one at 20 megahertz, and another one at 5 megahertz here. And all you need to do is, in the carrier aggregation application, select each of these component carriers in turn and configure the frequency and bandwidth. That's all you need to do. And then the unit will scroll through each of these component carriers in turn and report all these measurements for you. So whether or not it's MIMO and what the MIMO configuration is, what configuration of cyclic prefix, the reference signal power, sync signal power, modulation quality measurements, and importantly, as I've said, the time alignment error here between those component carriers. So that's all you need to do. Configure the component carriers for frequency and bandwidth, and all the measurements will pop out automatically. Now, what happens if you find you've got a problem on one of these component carriers? Well, let's say we have a problem on component carrier 2 here. All the user needs to do is go back into this menu here, select component carrier 2, so the red dot is against here, and then you could select any one of these measurements like scanner or TX test or mapping or any other measurements here for RF and modulation quality, and it will go back to those measurements and tune automatically to the frequency and bandwidth of the component carrier you've chosen. So very convenient to go backwards and forwards between overall carrier aggregation measurement and looking specifically at each component carrier in turn. Nice and convenient, easy to use feature for carrier aggregation measurements in the field. Another quick measurement I want to talk about is probably a retrospective measurement in a lot of cases. And it's to do with geolocation services required in VoLTE application. One method for determining the position of a UE or a subscriber in, say, an emergency in a 911 situation or a 112 situation in Europe is to use some kind of delay measurement. The user equipment itself measures the delay of reference signals generated in the baseband unit. And if it takes those measurements from 2 different cell sites, so it can measure the relative delay between 2 different cell sites, it then knows that the user is somewhere on a hyperbola path in the cell area. Now, if it takes another pair of readings from 2 different cell sites, it will generate another hyperbola curve, and where those 2 hyperbola curves intersect is where the user is likely to be. So it does rely on accurate timing measurements of those reference signals. Now, the delays are actually measured from where the signals are transmitted from the antenna. But of course, the reference signals are generated way back in the baseband unit over here. So therefore, there's a delay from the baseband unit through the fiber and through the RF feeder cable antenna, which needs to be compensated for to make sure that the accuracy of where the user is maintained. So Anritsu has now provided in its DTF function for cable analysis a direct measurement of time delay, so that the time delay through the feeders here and through the GPS cable can be automatically determined, so it can be compensated for, so the delta timing of the reference signals can accurately determine where the user is in a 911 situation. So that's probably a retrospective measurement that has to be done on a lot of traditional cell sites, because when they were originally installed before VoLTE came along, that measurement was not done. The other measurement I want to talk about quickly is DAS integrity testing. DAS meaning distributed antenna systems. I alluded to that earlier on, especially with LTE. More and more DAS systems are being installed. It's an unfortunate fact that most buildings on the planet today were not designed with internal RF communications in mind. Obviously, new buildings that are being designed and built today certainly are being designed and built with internal RF communications in mind. So this situation hopefully will get better with newer buildings. But in order for signals to penetrate within buildings, it's more efficient now to move the base station inside the building and to distribute those signals around the building in some way. So what happens now is that the radio cabinet with all the radios for the different technologies that need to be distributed is housed inside the building, and RF cables are then sent to an RF combiner where they're all combined onto the same feeder and then distributed by coax to various parts of the building, and then via antennas to illuminate various parts of the building. This one on the left here, this is what we call a passive DAS system, where you have RF generated here through an RF combiner, and then the signals are generated in the RF environment as well. Down here, in this scenario here, we have what's called an active DAS system, where again you have the radio cabinet with signals being distributed to an RF combiner, but now the combined signal goes through some kind of media conversion, usually RF to optical, because the losses are less. So here we have RF signal being converted to an optical signal, and then as it gets distributed throughout the window, throughout the building, the reverse happens. It gets converted back to an RF signal for local distribution on a particular floor in the building, for example. Now, these media converters are pretty simple, basic things. Basically, it's taking RF energy, and that RF energy is modulating the light here in an analog way. So all you've got along here is light that's being modulated with RF energy. There's no digitization going on, nothing like that. It's just straightforward RF modulated light. So then, as I said, when it gets up here, it then gets converted back to RF for distribution. Now, DAS systems are notorious for coverage problems, for interference problems, because the potential to produce external PIM is very, very high because of the structure of the building, the metal structure of the building. If an antenna is illuminating some kind of metal or other objects within the building, it's likely to cause PIM, which will be reflected back and cause receiver desensitization. The other thing as well is that these media converters in active systems can cause degradation to the signal. Now, on one of Anritsu's test equipment, the BTS Master, there's an option for a vector signal generator. So that could be used, if you like, to generate a reference signal before the combiner here. The modulation quality of that reference signal can be measured here, and then with another piece of equipment can be measured at the various tap-off points throughout the building to check for the integrity of this conversion from RF to optical and back again. Often these DAS systems are installed before the radio equipment is there, so that's again a nice technique that can be used using the vector signal generator to generate a reference signal, a golden reference signal, and to check the integrity of that signal at the various tap-off points throughout the DAS in the building, so that you know that the system is working correctly by the time the radios are installed. And of course, you can do a PIM test of both these systems as well, passive and active, before the radios are installed, if required. So that's a feature of 3G and 4G DAS systems to be able to get better coverage within buildings. The radios are installed within the building and then distributed using DAS antenna systems. Okay, well, I think I am coming to the end of my presentation. Just to let you know that, of course, Anritsu provides many, many handheld equipments, multifunction equipments or specific equipments to do various measurements that I've just described. And you're welcome to look at our website to get further details. And I'll hand you back to Kyle now to answer any of your questions.
Thanks, Andy. That was a great, very informative presentation. We had a few questions come in, and it looks like we have time for a couple of them. So the first one is it better to adopt the philosophy of routine preventative maintenance or take the fix after failure approach?
Yeah, $64,000 question. I guess from a test equipment manufacturer's point of view, I would say the former, preventive maintenance, but there are really good, sound business reasons why that is better. One of the measures that are in the public domain relate to customer churn. So on a regular basis, churn figures are published for each operator in various different countries around the world, along with things like coverage issues and latency issues and all that kind of stuff. Customer or subscriber churn is a big issue because what that means is you'll see numbers like 1% or 2%, sometimes even higher than that. Now those are monthly churn figures. So if you compound that over a year, if you have a monthly churn figure of 2%, that means that an operator is losing potentially a quarter of its subscribers every year. Okay, simply because of churn. Now there are many reasons why customers churn, but 50% of customers churn because of perceived poor network quality in terms of call drops, denied access, and throughput issues. So therefore, in that example I gave you of a 2% churn, 1% of those customers are churning because of perceived poor quality. It's no coincidence that operators who are using a preventative maintenance philosophy are demonstrated to have the lowest churn figures and therefore the highest network quality. And the old adage, it takes 6 or 7 times the cost to get more customers than to maintain existing ones. It means that that money that you use in your marketing dollars to get back your customers can be used on maintenance issues instead to maintain the customers that you already have. Also, it can mean that with preventive maintenance, you can detect potential failures before they do become issues in the field, because you can monitor trends. If you use a fix after failure, you've already got a problem. Customers are already noticing the poor quality because you've got a failure at a cell site. Preventive maintenance means that you can predict when failures are going to happen and make sure they don't happen by taking a preventative approach. Hope I've answered that okay.
Yeah, I think that was great. Thank you. Next question we had, it pertains to the slide 36 on the MIMO verification. What is the level of loading here for all of the 3 EVM values?
The level of?
EVM values pertaining to slide 36.
Okay, those EVM values, that EVM is related to EVM measurement on a broadcast channel. Okay, when the unit detects a MIMO signal, it switches to doing EVM measurements on the broadcast channel. The reason for that is that if it tries to do measurements on the actual data itself, because we don't have, a MIMO receiver, i.e. a multi-receiver input on the equipment, it will show bad measurements because of co-channel interference. However, the control channel, specifically the broadcast channel, is transmitted using what's called a transmit diversity mode, and we can decode the transmit diversity using a single receiver to give you good EVM measurements on the broadcast channel. So it's related to a QPSK measurement on the broadcast channel, if I've understood the question correctly.
Yeah, no, I think that was the answer they were looking for. We have time for just one more question, and I think we'll leave it with kind of a forward-looking question. So, Andy, what future trends do you see in the mobile communications arena that present the biggest challenges to a test equipment manufacturer?
Oh, I think, I think that the fact that operators are really hammering on reducing costs, I think what's going to happen is that the maintenance procedures are going to be de-skilled even further. And that puts a real onus on us to make our equipment even more user-friendly and foolproof and to be automatically configurable. I think the skill of maintenance technicians out there is quite high at the moment, but I think going forward, in order for the speed of rollout for LTE to be required, I think the maintenance techniques and the technicians are going to be less skilled than they are today. So therefore, as I said, we have to make sure that our equipment is easy to use, automatically configurable, and adaptable to the new configurations and the new base station techniques.
Great. That's all the time we have today. I want to thank everyone for attending Adapting Maintenance Techniques to Current Trends in LTE Installations, presented by Anritsu. Again, our presenter today was Andy Stanton, Product Manager at Anritsu. Thank you, Andy.